Hey folks, welcome to Stats with Sai. In this video, we'll be deep diving into multiple linear regression, one of the most powerful and widely used techniques in data science. So, before going into coding, let's just see what multiple linear regression is, like in brief. So, multiple linear regression allows us to predict a continuous variable, that is a dependent variable, based on multiple independent predictor variables. So it helps us understand how several factors simultaneously influence an outcome, like a dependent variable. So the core concept of multiple linear regression is so it extends beyond the simple linear regression where to include multiple predictors or multiple independent variables. So this is the form of mathematical form of simple linear regression y equal to beta naught plus beta 1 x plus error, and the extended version of simple linear regression is a multiple linear regression, we can say like that in a simple way, where we have instead of one independent variable or one predictor, we have multiple x1 x2 x3 and multiple coefficients for the same, and we have an error term and a intercept. Here in these terms, y is a dependent variable, what we are trying to predict, like what is our interest in, and beta naught is the y intercept, like the value of y when all x's are 0, and beta 1 to beta n or beta p are coefficients representing the change in y for each unit change in corresponding x variable, while holding all other variables constant, meaning for one unit change in x, as in x is our predictor for independent variable, uh, what is the corresponding change in dependent variable. So that's how coefficients are interpreted. And x1 to x1, 2, 3 are predictor variables, and e is error term. Now, why is it useful for us? Uh, and in real world, the problems are complex. So most outcomes are influenced by multiple factors simultaneously, not just one independent variable. And controls for confounding. Like by including multiple variables, we can isolate the effect of one variable while controlling for others. And the better prediction, like generally, like models with multiple predictors tend to make accurate predictions than models with single dependent and independent variables. And what are the key assumptions for a multiple regression model? So it assumes linearity, meaning the relationship between predictors and outcome or independent variable and outcome variable or dependent variable is linear. And the second assumption is independence. So the observations, whatever the observations are made, those are independent of each other. Homoscedasticity, like the variance across the error terms is constant across all levels of predictors or all across all levels of independent variables. Normality is like the residuals follow a normal distribution, and multicollinearity, like there should not be any multicollinearity, meaning all the independent variables are not highly correlated with each other. So these are the this is the brief intro to what multiple linear regression is. So in this video, instead of any like simple boring example, we'll try to predict something like fun like what factors influence number of views on viral cat videos on social media. So that is what I'm trying to do in this model. So by the end of the video, I hope you'll be able to understand like not just how to run a multiple linear regression model in Python, but more importantly, how to interpret the output, like interpret each aspect of the output of your model. So that is what I'm trying to demonstrate through this video. So yeah, if, let's get coding. Now I will create a data set, an artificial data set. I'm not importing any data set or existing data set. I'm just, for the sake of demonstrating, I will be creating a data set with known relations. And before creating data set, let's import all the libraries that are required. Import libraries, import numpy, pandas, matplotlib, seaborn, scikit-learn model, scikit-learn models, try not yes. Google is Google AI is already giving the code. Also import stats model. We will do it with both stats model and scikit-learn. Stats models. OLS ordinary. So these are all the libraries that we need. Now let's create a data set. I will divide this into parts. Maybe I'll just do it as a text. Let's make it bold. That field. This ensures to keep the data set same across multiple iterations so that we don't get different results each time we run the code. So I'm taking a sample size of 100 here. Let's generate some features. Now, what are the factors that can you know, influence the number of views of cat videos on social media? Let's just say, start with length of video length. I'm creating a random normal distribution for video length with mean of 3 and standard deviation of 1 for the sample size of 100. Video length in minutes. Now, now let's create another feature that might influence the number of views. Or let's say we have a score for cuteness. Again, we are doing a random integers between 1 and 10 for our sample size. We are doing it, no, like we are creating a cuteness score of 1 to 10. And let's say number of cats in the video also influence the number of views. Simple will do, yeah, number of cats in the video and if we say if are there any funny moments in the video. This is one factor that might influence. Again, we'll take some 8 instances, number of funny memes videos. And what is there any influence of upload time, like when the video is uploaded? Again, we'll do generator random integers like from 0 to 24 hours for the whole sample size. So we are generating hours of time of upload. 0 to 23 hours. Now let's generate a target variable that is our number of views. Views is equal to, let's create some known relationships for us. We have 50,000 views. This is a known relationship I'm defining. So this is a synthetic data set, like a artificial data set I am doing. So it can differ from, and the numbers I'm taking as it because I know I will be knowing the relationship so that I can verify the our outcome. Let's say shorter videos are getting like more, more views. Short videos get more views. Option for cuteness 3000. Cuter videos get more views. More cats means more views. Let's give it 20,000. And more funny moments, more views. 15,000. Upload time. Let's say upload time. Yes. So we'll say, we'll say videos uploaded near no are getting more views. So this is my assumptions so that I'm giving a such relation. And at the let's add a bit of randomness to mimic the real world problem. Distribution will be some random noise. Now we created our target variable, dependent variable. Now let's ensure that whatever we created all are positive values. Views is equal to create a create it as a data frame. PD pandas cuteness cats views. Yes. Now we have our data frame, and let's see how our data set is working. First few rows of our data set. Now that it should show us our data set with our known relationships that we created. So this is the first few rows. So we have video length, cuteness times, upload time, and views. We created a dataset with 100 simulated cat videos, and for which each video we created video length in minutes, cuteness score from 1 to 10, number of cats in video, number of funny moments, and time of upload, hour of upload, and the number of views. And intentionally, I've built some relationships like shorter videos get more views, cuter cats also get more views, etc. And also, I added some randomness to mimic the you know, real world situations. So yeah, this is our data set. Now let's explore the data, whatever the data we created. Let's see how it is looking, exploring the data. So before we build our model, so let's explore our data to get a better understanding of what kind of data and relationships that we are working with. Let's run some basic statistics. basics of our data set. Describe is the function to get the uh, basic statistics. So we have it gives us mean, standard deviation, minimum, like what is the 25th percentile of data looking at 50 second point, 50th percentile, 75th percentile, and maximum. Well, now let's prepare a correlation matrix of each data set to better understand. Correlation matrix of our data set. It gives us how each variable is uh, correlating with the other variable. Let's create a heat map, correlation heat map. Correlation matrix of our video features. Let me create a different variable also for this. So this is the correlation matrix. I'm limiting the distance to 2 points. So this is the correlation matrix of video length, cuteness score, number of cats, funny moments, upload time, and views. Now let's also create a pair plot. So this gives us the relationship between features and views. Yeah. So this gives us the relationship between features and views. How video length is related, cuteness score is related, number of cats, funny moments, and upload times. So yeah. Now the correlation matrix shows us how each feature relates to the number of views. Now, if we notice, um, yes, where is this is view for this. Now, cuteness factor. Cuteness factor is like has showing a high positive correlation. So we can say that like people love cute cats. Also, and video length is showing negative correlation. That means the longer the video, the number of views might go down. So shorter, like people tend to prefer shorter cuteness videos. And remember that these are the relationships that I intentionally built into the data when I'm creating the data set. So if we get a realistic like real world data set, these variables might relationship might be different. But for this model, I built the data set so that I put in the intentional relationships like this. And the pair plot also shows us like different how views are related to the like video length 1 minute, 2 minutes. So yeah. Now let's build a regression model. So we'll use both Scikit-learn and Statsmodels. While Scikit-learn is great for prediction tasks, Stat models gives us more detailed statistical information about the model, so that I will demonstrate it in both Scikit-learn and Stats model. Let's split the data into training and testing sets. Data, train, and testing set. Now here our X is predictors and Y is our outcome independent predictor variables, outcome variable. Sorry. Now, yeah, train test split gives us like splits the data into training and testing data sets. So we are splitting X and Y into train and test. In test is 20% of data and train is 80% of data. So like we use 80% of data to train our model, and we will test the model with the remaining 20% data set to check like whether the model is performing well or not. So this function xtrain test split, sorry, train test split gives us splits the data into training and testing registers. First, let's use Scikit-learn model and we are fitting it with to the uh, training data set. Training, let's make predictions with test data set. And we will evaluate the model. For this, I think we already imported from the beginning. Fine, let's just see how it is. MSC mean square error, y test y print, r square, y test y. We will print everything. Mean square error. Also will print r squared. Sorry, will print the coefficients. Also, we will print the intercept. So we will run the stats model also. Um, extreme is not stat. Let's keep it. Okay, and let's leave it like this. Um, let me type it again. Let's add constant because it doesn't add a constant automatically the model. Great. So great. We have split our data into here training and testing sets, built a model using Scikit-learn, and then we created another model using stats models to get more detailed statistics of the model. Yeah. Now let's see how our results are. Let's run this. This I didn't try for the anyway. I've imported it earlier, so it should be running. Yes. So this is the output that we are getting from our both the models, scikit-learn and Statsmodel. Now, for the most important part, that is interpreting the result. So let's go through each component of the stats model output. So first we'll see the model fit statistics. Let's say we are, what is the R squared? Yes, is this much. So this tells us around 48 or 48.5% to be precise of the variation in the views of videos can be explained by our model. So although this is very less variation, 48.5%, so like ideally it should be more. And since this is the dataset that I created, maybe it is showing less R squared. And so let's see the other parameters also. Now we have adjusted R square this much. This is adjusted R square. What does this mean? This is R squared adjusted for the number of, since it is close to the model, we didn't overfit our model. And this is R squared adjusted for the number of predictors. And it is close to R squared. So we didn't overfit our model. Now what is overfitting? It means the model, like our model didn't learn too much on the training data set. It means like it won't, it performs well on the training and test data set, but it won't give reliable results when it is exposed to new data sets. So yeah, like it learns very well on the training data set, but when it is used for a new data set, it won't give like very reliable results. So that is what overfitting is. And next output we will be checking is F statistic. Our F statistic is 17.73. So what does this mean? This tests whether at least one predictor variable has a non-zero coefficient. So our high F statistic with a p-value of p-value of less than 0.05 tells us our model is statistically significant. So high F statistic with a very low p-value, like it's almost 0.00 types. So it tells us our model is it tells us our model is statistically significant. So here is the probability of p-value of F statistic. This is less than like 0.005, right? Like into 10 power minus 12, 2.45 into 10 power minus 12. Now, let's see the coefficients. Constant is the intercept. This is expected number of views when all our predictors are 0. So if all our predictors are 0, this is the number of views that are expected, minus 2.434 into 10 power 4. So that is like around minus 2400 views or less views. And next is video length. So video length is for each additional minute of video length, we expect views to decrease by almost this much, like 1.583 into 10 power 4. That means like 15,000. For each additional 1 minute more length of video we are expected to lose at least 15,000 views for each 1 minute, additional 1 minute. And the p-value is uh, more than 0.05. So it is not statistically significant by this model, or this other, we can say that this what do you say, this variable is not statistically significant, or we can drop this from our model. And cuteness score, we have each point increase in cuteness score gives us more than like around 29,000 or around 30,000 views for each point, each 1 point increase in the cuteness score. So it is all this is statistically significant. And we have funny moments. Also, sorry, number of cats. Number of cats also statistically significant. So for each, like increasing one unit of cat in a video, like if you have two videos, sorry, two cats, three cats, like by increasing cat number of cats, you can increase the number of videos. So by increasing one cat in your video, you will be able to get around 28,000 views, more views, and funny moments. If by having like one unit of like by each additional funny moment adds about 19,000 views. And upload time again is more than 0.05 means it is not statistically significant. So we can drop this, you know, variable. So let's do one thing. Let's drop these two variables which are giving us like statistical insignificance or not significant for our model, and run the model again and see how these remaining are perform. Video length and upload time. See, after removing the variables also, we are getting these almost same r square and just r square. So the variables are not like the variables not are not contributing for anything. Like adding or removing those variables does not make any difference in for our model. So we can retain those variables. Video length, and we have upload time. Although these are statistically insignificant, not significant, these two variables, but the end result is not making any uh, like better model. So we can retain those variables. Now, this standard errors tells us about the precision of our coefficient estimates. Like the smaller the standard errors, it indicates more precise estimates. Let's plot our results and see how they are against the actual, sorry, part 5, visualization of results. So let's visualize our models predictions versus the actual values. So actual values are like we already defined the relationships and the number of views. So let's just see how it is performed. Character plot. Also plot residuals. Residuals equals this. Let's give binary plot. So let's talk about feature features are important. Coefficients is equal to beta frame now. Let's run this. So these visualizations help us understand uh, the model's performance. The scatter plot of predicted versus actual values shows us how close our predictions are to the reality, or like to the dataset that we created. And the residual plot helps us check if our linear model is appropriate. Like ideally, residual should be randomly scattered around the zero with no patterns. And the feature importance chart confirms what we saw in the coefficients. Like cuteness score has the biggest impact on views, like followed by number of cats and funny moments. Let's run it again. Name. Yeah. Well, let me just write this again. Yes. Mm, good. Well, let me just do it separately. I will do three red plots. This is actual versus predicted. This is residuals, and this is feature importance, right? Let me make it a bit smaller. Six, four. Yeah, great. So yes, this shows us actual versus predicted values. The red line shows the actual values, and blue dots or blue point shows um, this thing, predicted values. The scatter plot of predicted versus actual shows how close uh, this are predicted values to the actual values. And this is the residual plot. It should be like randomly scattered to like this helps us check the linearity of the model. So from this plot, we can say that the model linearity is appropriate, as ideally residuals points should be scattered randomly around zero with there is no pattern, like there should not be any pattern. And from here, we can see that what are the important features. So first number of cats, then cuteness score, and then funny moments. Upload time has a little bit, but video length is the more it goes, the less the views are. So yeah, now so what it means for anyone like from this model, what do we try? What are we trying to say? So it's we are saying that make videos shorter um, and feature that feature cutest cats so that you can find like more views and feature put more than one cats and create funny moments. Although and upload time has a little bit of impact, but that is not much. Still, you can upload it around the time, like around noon time to get more views. So this is the output of the model that we created. But just remember that this is a model based on a artificial data set, the data set that I created. So in the real world, you will have to collect the real data set and refine your model over the time with like what are the variables that should be there, what should be removed, dropped, uh, like that. In conclusion, what did we learn in this video? So created a data set about cat videos, built a multiple linear model, three like model using Scikit-learn and Statsmodels. It interpreted each component of the model out, and we visualize the model's performance and understood the importance or relative importance of each feature. Now, yeah, I hope this. Now, I hope this example made multiple linear regression, like understanding the multiple linear regression and running the model a bit more intuitively. And if you like this approach to understand statistical concept, just hit the like button and subscribe for more data tutorials. Thank you.